The purpose of this lab was to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. In this case, the object dropped was a styrofoam ball with a diameter of 6 inches. In this lab, Newton's second law is applied to data found in Tracker, which was gathered from the ball's fall, in order to determine how outside forces affect a ball's movement in the air. Initially, gravity is the only force accounted for, but as that overestimates the position, an additional force, turbulent drag, is taken into account. To begin, a video of a ball being dropped from the top of the ceiling that fell straight to the ground is captured and uploaded to Tracker, a data analyzing tool. It is then analyzed to produce a position versus time graph for the ball, as well as a chart with the same data. The position points are calculated in reference to the video by using a calibration stick that is set to the diameter of the styrofoam ball, which is 6 inches or 0.15 meters. Next, Newton's second law was implemented in the Python code. Newton's second law states that the net force of an object is equal to its mass times its acceleration, or change in velocity over change in time. According to Newton's second law, an object will only accelerate if there is a net or unbalanced force acting upon it. The presence of an unbalanced force will then accelerate an object. As the ball is not accelerating, F net is taken to be 0. However, just because our F net is 0 does not mean that there are not forces acting on the ball. This free body diagram represents the forces acting on the ball. In this experiment, the downward force of gravity and the turbulent drag force make up F net, and it is observed how these forces affect the object's position. From this knowledge, Newton's second law can then be applied to the observed data in order to calculate the gravitational force and the drag force. We'll start with using the gravitational force. To show the effects of gravity, a code is created in Python. First, the ball's mass is set to 0.051 kilograms. Then the ball's initial position and velocity are set to the 0 vector, as the ball was starting from rest. It is then confirmed that delta t is small, as the Python calculates position by using small increments of time rather than an average. And lastly, the end time is set to be 0.655 seconds, as that was how long it took for the ball to drop in the video. Lastly, the ball's position and velocity equations are put in terms that can be understood in Python, as shown here. Next, the Fnet in Python is adjusted. For this trial, Fnet is set to the weight or gravitational force. The equation for the force of gravity shows us that Fg is equal to the negative value of the mass times gravity. The code also includes j hat, which is just a unit vector for the y-axis, where the direction of positive y is chosen as the up direction. Then the weight is set to be a negative vector, as this free body diagram shows, so when an object is falling on Earth, gravity will always work to pull the object back down to the surface. On Earth, gravity is 9.8 meters per second squared. When the code is run, VIDLE produces this simulation. However, when the data from Python is imported into a graph of the ball's predicted movement, it is seen that in comparison to the observed movement when gravity is the only force, the position is overestimated. This is seen as the blue line, the observed position, is higher than the red line, the predicted position with gravity. Because our position is recorded on the negative y-axis, points closer to the origin will actually have traveled less distance than points that are further down on the y-axis. It can then be predicted that there are additional forces at play, and so it is necessary to calculate the turbulent drag force on the ball. In order to calculate the drag force, we must change the code in Python. First, Fnet is changed to include both the weight force and the drag force. Unlike the force of the ball's weight, turbulent drag force is always opposite to the direction of the object's motion, and the magnitude of the turbulent force is proportional to the square of the object's speed. Therefore, we make up this formula. In this equation, B stands for the proportionality constant, which is then multiplied by a vector of the ball's velocity squared. This is done by first maintaining the original sign of the velocity so that we will not change the velocity's direction, and then squaring the x, y, and z velocity components. The proportionality constant, B, was calculated by means of plugging in values and then seeing where the ball's final position was in comparison to the observed final position. The B value that achieved the closest match to the observed final position ended up being 0.00372. With this B, the Python code produces a set of points that when graphed show a correct trend for the ball's predicted position. The orange line shows that when both the drag and the gravitational force are included, the predicted position is much more accurate. As shown, the blue observed line nearly lines up perfectly with the new predicted position orange line. Differences between the two lines can be accounted for in the method that B was calculated, as it was just a system of guess and check, as well as the fact that the styrofoam ball that was being dropped was not perfectly round, which could affect the ball's straight path of downward travel. What does it mean? Terminal velocity of a falling object is the velocity of the object when the drag force equals gravity. Due to the fact that our Fnet is equal to 0 and that it is made up of only the drag force and gravity, it can be deduced that the drag force is equal but opposite to the force of gravity. Thus, it can be determined that the model that includes both drag and the force of gravity predicts the terminal velocity. When examining the data from the observation model and both prediction models, it is inferred that the velocity is constant by the fact that acceleration is the change in velocity over the change in time. Considering the fact that the object has a constant acceleration, gravity equals 9.8, and our delta t is set as a small increment in time, it can be assumed that the velocity is constant. What if? In further examining terminal velocity, if the ball has initially been thrown downward, the terminal velocity would be the same in comparison to the case where the same object is initially dropped from rest. This is proven by simply looking at the equation for terminal velocity, which does not factor in the ball's velocity, but only its mass, gravity, the proportionality constant, and c. This is further proven through the Python code. When the initial velocity is changed from 0 to 100 and the code is run, the object's position at 0.655 seconds does not change. In this graph, the green line represents the object at an initial velocity of 100, with the blue line being the observed position and the predicted position with drag in orange. As you can see, the green and orange lines lie exactly on top of each other, proving that there is no difference in the terminal velocity. In conclusion, it can be seen that when an object is falling down, there is both a gravitational force as well as a turbulent drag force acting on the object. Thanks for watching!